Hello, 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 hello. Hope I'm audible. Okay, so let's start. So, hey everyone, this is Devansh here, and today we are going to discuss beautiful problems of the contest, Division 2, Codeforces Round 1078. This was actually a very good round. We had, I think, 6 to 7 problems here. Yeah, we had 7 problems here, and like we are going to discuss the first five. I have solved the fifth one, and during contest, I did four. So yeah, it was great contest. Someone said I'm not audible clearly. Someone said I'm not audible clearly. Okay. The secret message. This one, uh, like around, yeah, this would be around 1500 to 1600. I'm not sure. Someone said in the comments D was unexpectedly easy. Yeah, actually D was very easy compared to C. Like and B even like even B was little tricky. All those who are live, you can actually ping out in the comments. I'm actively watching comments in regular intervals. So yeah, I'm audible clear. I hope I'm clearly audible. And now let's start. So yeah, let's start one by one. So how are we going to discuss the problem? First, we will extract whatever we could from the problem. Thus, we are going to read the problem and we are going to understand like the problem itself first. Then we are going to check out the examples and understand the problem more. And then we are going to go towards observations and intuitions. What observations we could have from the problem and what intuitions we could have. And then we are going to at last jump towards the solution. From the observations and intuitions we got along the way, we are going to drive the solution and then we'll see through the code and then the problem will end. Huh. Right? So yeah, someone said that I didn't understand how to solve be optimally. Okay. Great. Great. That's why you are here. Right? Even if you think like if your solution was better in any of the problems, you can ping it out in the comments, right? I'll be actively watching comments after the stream too. So that would be great. Okay. Let's start the problem. Okay. Yeah. Let's start from the very first problem, lawn mower. Okay. The exit from the summer cottage is fenced with a fence consisting of N boards, each 1 meter wide. To the left and right of the exits are fences of other plots. Okay, 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 okay. This is the very first problem, right? So, yeah. Some of the boards of the fence wanted to be removed for construction of a bathhouse, possibly all or none. While there is automatically mower on the plot that is W meters wide and must not leave the plot through a hole in fence. Okay. The lawnmower will able to exit the plot if there are at least W consecutive removed boards among the numbers of the removed boards. Determine the maximum number of boards that can be removed from the fence. Okay, great. Okay. Yeah. So what this problem says that we have a fence. Let's assume this is our fence. Where, okay, this is our fence. Where each of this, right, each of this board, these are boards, right? These are boards. These are 1 meter wide. Got it. These are 1 meter wide, and the left side of fence is some other fence, which we cannot uh, do or modify. And on the right side of this fence is also some other fence which we could not modify. Right. And we also have, right. And we also have a lawn mower, which is W meters wide. Got it. So this is fence. Second thing we have is lawn mower, which is W-meter wide. Assume this W is stands for the size or the width of the lawnmower. And what we have to do is we can remove some number of boards here. Right, right. We have to find the maximum number of boards that we can remove from the fence such that this lawnmower cannot go outside the fence. Got it. This is like how visually we could do it. Right. This is like a very, again, this is very classic. Like we can remove some number of boards. And if by any chance we remove boards such that this lawnmower can go outside, then we lose. Right, right. So what we can do, like how many number of boards? This is the third point that we got from the question. Find maximum boards we can remove. We can remove. Right, 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 right. So this is the entire question. The first question tells us that this fence has few number of boards, right? And that is denoted by n, right? Each board is 1 meter wide, and we have to find what is the maximum number of boards that we could remove such that this land mover, which is W meters wide, cannot go outside, right? This is what we need to find. The very perfect example has already been shown here in the example, right? The first example says that we have 9 boards. The input says that this is the classic t number of test cases we have, and then we are given two integers n and w. N is the total number of boards we have, and w is the width of the mower, right? So let's actually discuss the first test case, which is beautifully depicted in the example here. How? Here there are n boards, right? And the size of mower is 3. What does this tells? That we cannot remove, by any chance we cannot remove 3 consecutive boards, right, right, right. Because if we remove these, let's say this w is equal to 3 here, if we remove these consecutive boards, the mower can go outside, right, right. So this is the first observation, which is if we remove w or greater than equal to w boards, or consecutive boards, right, boards, right. We can, if we lose, winning and losing, right? If we remove w or w consecutive boards, what is going to happen? The mover can go outside, right? Because here in the definition it's been uh, told to us that if this meters like the plot, there should not be a gap of w meters wide, otherwise it will move. it will go through the hole and it will go outside, which we don't want, right? Right, and we have to find out how many boards can we remove. So it's like pretty obvious thing, right? We can remove the first, second, but if we remove the third one, what will happen? What will happen if you remove the third one? We will lose. So let's keep it and then do it. We can do it greedily, right? Is the first intuition that comes to our mind. Even in the example, let's see how he has done it. Even he has make sure that he does not keep three or more consecutive boards, right? He do not remove three or more consecutive boards. How many consecutive boards can he remove? He can only remove two, right? At max two. So he has removed two boards as much as he can, right? So this is our second observation. What we can remove maximum k minus 1 more boards consecutively. Right, right. Anything in the comments? When will the rating be updated? I don't know. Even in like, I think even we cannot submit our solutions right now because there is some maintenance. Like if you read it, it was from 4 o'clock, I believe. I did brute force on first one. By not counting I percent W got TLE, took time and got the simple maths equation. Right. Yeah. We got two observation, right? We cannot remove W or greater than equal to W both consecutively. And we can remove max K minus 1 consecutively. Right. So what we have to find is using these two equations. Using these two equations, there are two approaches. One is the maths one is the brute force one. Always when you solve any problem, always think how can we solve it brute force? We are going to discuss both. So brute force, let's say these are our boards and the value of k is equal to 3. How are we going to solve this? Right. Can we remove this? Let's remove this. Okay, got it. Can we remove this? Let's remove this. Got it. Can we remove this? Wait. We have to wait because if we remove this, there would be three consecutive ones, right? So we are not going to remove this. We'll keep it. Now again, now as we kept it, the counter is being reset, right? Now again, can we remove this? Yeah, we can remove this. Can we remove this? Yeah, we can remove this. Can we remove this? No, we cannot remove this. How many did we remove? We removed 1, 2, 3, and 4. So answer here would be 6 minus 4. 2 are left and 4 are removed. Right. We have to tell the maximum ones we remove, which is equal to 4. And 2 are left, right? But it's not required. We just have to tell how many we can remove. So brute force approach would be taking some variable, let's say counter. This counter would be equal to, let's say 3. At max, how many can we remove? Which was our second observation. We can remove k minus 1, right? So we'll keep this counter to k minus 1, which here would be 2. And after removing this, we'll reduce the counter by 1. Let's say the counter values here would be, initially we reduce it by 1, so the counter would be 1. We again reduce it, the counter here is 0. As it's 0 here, like when it reaches here, the answer counter is 0. We are going to keep this and update the counter. We are going to reset the counter to 2. So again, this would be 2. It goes here, it would be 1. It goes here, again it's 0. Again, as it's 0, we are going to reset it to 2. Again, here it goes here. Here it would be again 2. Again, if let's say we have the next block, can we reduce it? Yes. So the counter would be here 1 and we are going to remove this. Right. So we can use this brute force approach here. Otherwise, there's also a mathematical approach here that we can use, which is basically in maths. Can you think something? Can you understand something? We can actually calculate the number of blocks that we have to save, the number of blocks that we have to save, right? How can we calculate divided by k? These are the saved ones, which are not destroyed or not removed. If we got the saved ones, why? Like, because we have to calculate, right? How many, this is basically we are calculating how many length of three we have, how many, sorry, how many width how many widths of continuous blocks do we have here, right? The current width is W. This K is actually W, right? Just, it doesn't cause confusion, right? This is W, the width, right? So let's say we approach this, actually tells us how many least number of saved ones we could have. As this is least, subtracting it from the total number of logs would give us, and divided by K, the maximum logs we could destroy, right? Right, maximum boards we could destroy. We can destroy, right? Even I did it with the maths, because I thought, like, why use brute force? Can we use brute force here, by the way? No, we cannot, right? Because n is less than equal to 10 raised to power 9. So maximum value of n is 10 raised to power 9, right? We won't be able to iterate each log, right? As n is here less than equal to 10 raised to power 9, the brute force won't work. Would give TLE. And we are TLE eliminators. We have to eliminate the TLE, right? Not get it. So these are the two approaches for the first problem. This would actually give TLE. So this is actually the better approach. Here we are actually calculating divided by K or W, n divided by W, whatever you say, n divided by W, just for the sake of convention that is given by the problem, right? Because problem says the width is W. So here we are calculating the least amount of gates we could have. How are we calculating? We know that among W consecutive, we need only one. Among W consecutive boards, we only need one board which is alive, right? And we choose it the rightmost extreme, because the leftmost extreme is already protected, right? We choose the rightmost extreme. Again, in this block, we choose the rightmost extreme. And in, let's say, this block, it's not even needed because here it's already covered, right? So this is how the math worked, and we converted the brute force into math problem, right? Someone said it, I did brute force in first one by not counting every I percent W and got TLE. Right, you will get TLE here because N is less than the maximum value. N is 10 raised to power 9, and we can only perform around 10 raised to power 7 operations per second in C++. Right, and the we got 1 second there, so we also had tight constraints. Okay, what is the rating of B? Let's actually move to the B part. Okay, rating of B, I think it was a little bit ad hoc type of question. It would be around 1200 to 1400. It could be even less because most people who didn't use their, like, who didn't thought through, went with the brute force approach, which was basically checking for each log how much we could get the maximum value if we basically transferred all the operations into one. Right, let's actually read the question, get through the question, and then we'll discuss about the rating of the problem. Right, I thought it would be around 1000, like 1000 to 1200, but I found this actually a little tricky. I found this problem a little tricky, like comparatively to C and D. For D problem, D was pretty easy. Even C was actually a pretty good one. Like compared, I would say C was harder than D. Let's actually not go there and first discuss the problem itself. So yeah, hope you understood the A problem. If you have any doubts, it was like pretty cliche problem. If you have any doubts, you can ping it out in the comments. Even after the contest, I'm going to read the comments. So yeah, if you think you still have doubts, you can ping out in the comments. Let's understand the B question. So question name is offshores. Okay, great. We have 1.5 seconds and 256 megabytes standard. Okay. Mark loves money very much. Okay. He keeps most of it in the bank. He stores his money in n different banks. The ith bank has AI rubles. Okay, great. So basically, okay, this was the first problem. Now let's move to the second one. Right. What we got from this line that he has n different banks. N banks, right? And each bank here is represented by an array of length A, right? So we eventually have dot A, right? And each bank has this many rupees. Each bank, this is a first point of the question that we got. Now, the second point is each bank AI rubles. Got it. This is the second point. Okay, got it. We got it. Now, one day, Mark decided to gather all his money in one bank. So he will transfer the money from one bank account to another one. Okay, great. All interbank transfers are arranged in the same way. Great. He can transfer only X rubles in one transfer. And considering all fees, Y rubles will be credited to the another account. Since bank wants to make profit, he holds that Y is less than equal to X. Okay. It is it's possible that Mark will not be able to transfer all his money to one bank. But he wants to find the maximum number of rubles that he can end up in any bank. Okay, great. Okay, great. So what we could do, what this tells us is that he wants all his money in one bank. Like he wants, but that's not might be possible, right? But there is this transaction he could have. Transaction. First, we are given the transaction. Let's call this transaction an operation, right? We are doing CP, right? Everywhere we perform some operation. Operation tells us that let's say we have this bank A and we have this bank B. We can transfer only X amount from A, and here when it reaches B, this amount something would be deducted, right? Some there would be some transition fee or like some bank service fee or something, and the B will be credited with Y. Got it? We at one transaction we can send X amount of rubles, but the person we are sending will only receive Y. Right? How much money did it we lost? We lost X minus Y, right? Because X should be transferred here, but X is not transferred. Y is transferred. And we are make sure that Y is always less than equal to X, right? Because the fee will only cut, right? Fee might be zero, right? Otherwise, there might be some fee that we are paying. That's why on the final transaction, he only receives Y. Okay, great, great. We got it. We got it. Now was the fourth thing what we need to find, right? The problem also tells us what we need to find. So we need to find max money any one bank can have. Can have. Okay, great, great, great. Right. This is we what we need to find. Max money any one bank can have. Okay. Let's also read the inputs. For each test case contains multiple test cases. This is like the standard. We are giving the standard T, which is the number of test cases. Then we are given three integers n, x, and y. The number of banks, the transfer amount, and the credited amount. Okay, great, great. And then we are given n integers a1, a2, dot 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 an, right? The initial amount of rubles in each bank. Okay, got it. N is the number of banks, x and y are the transaction values that we could have, right? And then we are given n integers, each tells us the number of rubles we have or the money we have in each bank. Okay, great, great. And the sum of values would not reach 2 into 10, would not exceed 2 into 10 raised to power 5. Okay, this is also standard one. And we have to output the maximum number of rubles that can be opted in any bank. Okay, great, 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 great. So this is the entire question. Okay, now let's observe. Let's take some example. Let's take the example which is already been given here, which is this one. To 4, right? We are given x is equal to 5. And what does this question mean? Okay, let's actually understand it deeply, right? This means that here n is equal to 4. That means that how many banks we have, right? How many banks we have? We have 4 banks. And here x equal to 5 and y equal to 4. What this means is that at any bank, let's this is bank A. If we take 5 rubles from here to pass it into bank B, this bank B will receive only 4 rubles. Got it? This part is clear. Okay, great. Now we are also given 4 banks. The first bank has 10 rubles, the second bank has 9 rubles, the third bank has 8 rubles, the fourth bank has 7 rubles. Okay, great, great, great. And we have to find the maximum money we could have in any bank. Right. So what comes to your mind, right? Which bank it would be? Right, this is the first observation we have, right? Which bank? Right, we have to find the maximum money any bank can have, right? So how can this bank, let's assume this bank should have the maximum money. How can this bank have the maximum money? Right? It's pretty straightforward observation that if we remove, like if you made maximum number of transactions from this to this, then maximum number of transactions from this to this, and then this to this, we would have maximum money in this one, in this bank, right? Am I right or am I wrong? Am I right, right? So let's say we want to make this bank as much money we could have. We want to gather as much money as we could have in the first bank. What we could do? We could do one transaction here, right? Right? What would be this after transaction? We are going to reduce what is the value of x and y here. We can take 5 rubles from somewhere and place 4 rubles somewhere else. Yeah, sure, sure. Let's say we did first, this is our first operation. We did here. What will happen? This will become 4 rubles and this would become plus 4. Right? We reduced 5 here, we added 4 here. Right? We reduced 5 here and we added 4 here. Right? So this would be 8, 7. This would actually be 14, 4, 8 and 7. Okay, great, 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 great. Again, can we apply more operation on this? No, because this is less than 5. We can take 5 rubles from somewhere and place 4 rubles somewhere else. Right, right. So what we can do, but we can perform operation here, right? Let's perform operation here. So this would be minus 5. We are going to add plus 4 here. Okay, great. Now this, the number of rubles in each bank would be 14 plus 4 is 18. This remains 4. 8 minus 5 is 3, 7. Okay, great, great, great. Can we do any more operation here? Yes, we can. We can have, right? We can actually reduce this to, okay, let's do it minus 5. And again here, we are going to have plus 4. Okay, very great, very great. So this would be 18 plus 4 is 22, 4, 3, and 2. Can we have any more operations here? No, no, we cannot have. Right? We cannot have any more operations here. So what are we going to do? Is 22 our answer? Can we assume that 22 would be our answer? 22 is the maximum, like for this sequence of arrays, 22 would be the maximum sum we could get in any bank, right? Right, right. Let me also see the comments. What is the rating of B? I think it's 1000 to 1200. Modulo Max, your explanation is go. Thank you, thank you, thank you, Leon. And find an index at which modulo X is largest and add it to some. Okay. Run it loop. Okay, okay. Let's actually see what we are going to do. So, what's the answer for this? It's 25, right? But we are off. We are off, right? So that means this is not the correct bank, right? This is not the correct bank. That means. So which could be the correct bank, right? So what do you think? What do you think we should do next? Right? We calculated for this bank how much money we could got from the other banks, and similarly let's actually move forward. Right? Let's move forward. Let's check for 9 because the answer is 25. We just saw the sample case, right? This is not the answer. Okay, again 10, 10, 9. We have 8 and 7. Okay, great, 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 great. Let's actually accumulate here. Let's accumulate here. Okay, great. Can we do one transaction here? Okay, it would be 5. 9 plus 4 is 13. 8 and 7. Okay, great, 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 great. Can we do one more transaction using here? Yeah, we can. We can. We can. Let's do it again here. So this would be 10. This would be 17. This would be 8 and this would be 7. Oh, sorry, this would be 0, right? Let's correct it. Yeah. We did -5 here and we did +4 here. This is 17. This is 8. This is 7. Okay, great, great, great. Can we do any more operations? Yes, 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 we can do it. We can actually do it -5 here and we can add +4 here. So now this becomes 0. 17 plus 4 is 21. This becomes 3 and this becomes 7. Great. Again, one more operation we can see. Let's do it. Now the final sum is 21 plus 4 is 25, 3 and 7. Okay, great. Now it's 25, which is greater than 22. Right, which is greater than 22. Okay, great, great, great. That means that this bank, if we filled all the money in our second bank, which is better option. What does this tells? This comes to our first observation. Right. Our first observation is every bank, if every bank is the last bank, might have different money left. Different money left, right? For every bank, if it's the last bank, if it's the last bank, we might have different money left. We just observed here. If this one was our last bank, we took all our money from other banks to the first bank, we resulted in the maximum value of 22. But for the second bank, if we did it for the second bank, we reached to the maximum value of 25. So what we got from this, check for every bank. Our second observation. Right. We check for every bank. This is what we could do, right? We did all the different ways. What is the our problem said that we need the maximum money any bank can have. So we check for each position or we check for each bank. What's the maximum money it could have? Right. That's the thing, right? That's the observation, right? This is like this would cover everything, right? Okay, great, great, great. So this means that if I check for every bank, right? If I check for every bank, the maximum of all the values that we get at the end for each bank, that would be our answer, right? But how are we going to check it? Right. What would be the, again, let's discuss the brute force approach here. Let's go step by step. We understood the problem. This is the problem. We understood the example. We may, while just going through the example, we came through two different solutions, two different observations. We noted the observation. Now we are going for the solution, right? So what's the solution here? Let's start with brute force. Observing above these 2 points, these two observation, we got to know that we can check for every bank, right? Again, let's say we have 10, 9, 8, 7 as the money left. Again, we are just extending on the first test case. Here, again, just for your refreshment, x is equal to 5 and y is equal to 4. X is the money y is the money which will be given for transaction to be completed. So what would be the brute force approach here? We will take this bank in one iteration and check for each, for let's say we come across this element. We are going to do transactions until this is this is less than x, right? And then we'll, if it's less than x, we'll move to the next one, and we will keep on doing this. What would be your time complexity here, right? First we need to take one position, right? We are going to have n different values for the last. We are going to take, first we are going to calculate for this, then we are going to calculate for this, and then this. Okay. Yeah. So we have n different positions that we are going to travel, or n different banks that we are going to travel for it. Right. Okay, great. And then second we need to find is, we need to make iteration for all those banks which are other than it. Let's say we took this bank. Then for each value, for each bank other than it, we have to make maximum transactions, right? For let's say this, for this bank, and then this, and then this. How many other banks we have? We have n minus 1 banks, right? So we have to iterate through each bank, right? Other than the bank itself, to find the maximum money we could get in this bank. Okay, great. So this would be n into n minus 1. And also there would be some, let's say, uh, threshold we have to calculate to basically reduce this, to make to get how many transactions what we could do, right? But that can also be calculated in, let's say, constant time, right? How many transactions can we make from 7 to 9, right? One approach is basically keep on subtracting x, right, until this is greater than x, right? We keep on subtracting this. We can do with a while loop, but this is going to take a lot of time. How much this time? Let's, the maximum value we have for any number is 10 raised to power 9, right? So how much time it would take? It would take 10 raised to power 9 divided by x. As we are talking about brute force, let's optimize later. Got it? So this would be the time complexity for the brute force. Okay. Okay, great. But this one thing which is good about brute force is it's always yields the answer, but there is always some problem with it. The problem here is the time complexity. It's taking huge amount of time. How are you going to reduce it? Let's start from the last. How much operations? Let's say we took 10, again, let's 10, 9, 8, and 7. Let's say we picked this one, right? Let's say we picked this bank. How much operations can we do from 9 to 10? This can easily be calculated, right? We could just divide 9 by x and we would know how many operations can we do. These many operations we can do, right? Again, for 8 we can do 8 by x operations, and for 7 we could do 7 by x operations. Okay, yeah, this is very good. We don't need this. We optimized it to O of 1 time complexity. of one constant, this becomes constant, right? You optimized it. So what's the time complexity after this optimization? It's n into n minus 1. This is now optimization war. We got the observation, we understood the problem. Now what we have to do, we found the brute force. Now we have to optimize this, right? So the first optimization is we made this constant. Okay, great, great, great. But still there's a problem here. The problem is we are still going for each and every, we are finding out for each and every how many operations we could do. How are we going to solve this? How are we going to solve this? So the time complexity still here is n square, right? How are we going to make this less? How can we solve it? Okay. When we think it, we know that for any number, here we have taken x. The 8 will go 8 upon x operation, right? Yeah. What if we have taken 9? Still the 8, this 8 can give 8 by x operations, 8 by x transactions, right? To 9 too. It doesn't matter. The sender will give 8 by x transactions, right? And it will give total y into 8 by x money to any of them. That's the truth. Yeah, this is our third observation actually, right? This is our third observation, that this will give us definite money to any of those. And this can only perform a certain number of transactions, which is the value divided by x, right? So the value divided by x transactions can only be formed by any of the bank. Okay, great. So how can we use this new observation that we made to calculate it? How can we use this? So what we could do is basically, again for this bank, 10, 9, 8, 7. What is the number of transactions? Let's keep this total variable, total operations or total transactions. Total transactions, right? And we iterate it across all the banks and find the total number of transactions we could have. Okay. What this means, that let's say we are iterating from here. This can perform 10 divided by 5, 2 transactions, right? This can perform 9 divided by 5, one transaction. This can perform 8 divided by 5, again one transaction. This can perform 7 divided by 5, which is again one transaction. So the total number of transaction is 2 plus 1 plus 1 plus 1. This is equal to 5. Got it, got it. Actions, right? So this is equal to 5. And then what we could do is, when we are iterating, when we are checking for this bank, what we do is we reduce the total transactions minus transactions we had for this bank, because we are not going to transfer money from this to this, right? The money that stays here, the money which is here stays here, right? We are not going to make transaction again, because that's a lossy operation. That actually reduces our money, right? So what we are going to do, the total number of transactions, right? Total transactions made to this bank, made to this bank is equal to total transactions we had minus transaction for this bank, for this bank. Right, right. Can you understand this formula? The total money, how we calculated the total money we could have at this position. We calculated the operations each everyone could make. So we calculated total number of transactions that would happen here, right? And then we multiplied that total number of transactions by y to calculate the money we got, right? For each transaction we got, for each transaction we get Y rubles. Right. So these are, this is the main part of the solution. What we are going to do is we are basically going to accumulate all the total transaction. Here the total transaction was 5. And then using this, what we are going to do, let's say if this was a bank, this we have to check what if this was the bank, the last bank. So this would have money equal to value, its current value it has, plus transactions happened in it. Transactions, right, happened here into Y. Why? Why? Because Y is the action. So this is the value for this location. This can we calculate? Yeah, we can calculate by using this formula. The total transactions we made to this bank is total transactions minus transactions for this bank, right? Here, so the final value would be value plus total transactions. I'm writing total transaction as total trans, right? Trans, right? Minus transactions happened here, and this into Y. For this, what's the for this bank? What's the answer for it? This would be 10 plus total number of transactions we had was 5. The transactions that are going to happen is 10 minus x, which is 5, right? X, which is equal to 5 into y, which is equal to 4. So this would be 10 plus 5 minus 2, right? Into 4, 3 into 4, right? 10 plus 3 into 4, which is equal to 22. Does this match with our observation? Like does this match? Are we correct? Let's check. Yeah, here we calculated it was 22. Great. So yeah, we calculated it, and this is how we reached it. So this formula is totally working. Right. Let me actually go through my summation so you can understand much better way how we did it. Okay, here. So actually just here we are taking in the input. This is my template, by the way, right? Ignore it if you don't know what the template is, right? It's just template consists of functions basically. So in during the contest, if we need few functions, we could actually use these instead of going on the internet and finding out the functions, right? Or the classes, for example, or the data structures we need during the contest. So here we are taking in the input, got it. And here this total is the total number of transactions. So here we added the total, we founded the total number of transactions. And here's our formula. Here's a formula. This is the value, the total number of transactions minus the transactions this bank was gonna have into Y, the money we made in each transaction, and we are going to basically find the maximum. This is our temporary answer and this is our final answer. We are going to print it. This was how simple this solution was. Got it? So we just had to go step by step, right? So first we understood the problem. We just ran through the example, and then we came across few observations. Using those observations, we tried a brute force approach. The brute force approach was actually very costly. We reduced the cost of brute force approach by optimizing it. During this journey, we also found a few observations. We noted it. We made a the formula for calculating for each bank, and then finally we used the formula in our code. So this is how the entire workflow worked. Also, I think I forgot to show code for the first problem. So here it is. Right, let's two-liner code. Right, these are the total number of safe ports n minus k. That's why I didn't show, like it was just two-liner. Right. So these two. Now let's move on to third one. First, let me just check out comment section. If you guys think, if you guys want to discuss something, if you think you couldn't understand anything, let me just read the comments too. What's the rating of B? I think it's around 1000 to 1200. I think it's a good question. It's not that bad. So modulo max. Your explanation is good. Thank you. Find the index which x is largest and add it some. I think you're okay. Okay. Yeah. Okay. This is actually very beautiful approach, which is given by Magnus Fifth. Instead of calculating for each index, you must have noticed, right? We can calculate it for the person who had the maximum, for the bank which had maximum modulo x. Why modulo x? Something you must have seen while we were calculating our cases. If we are calculating for this bank, you money, like some money gets wasted, right? For example, in this one, the 3 and the 7 gets wasted, completely wasted. What is the 3 and 2 here? Actually, 2, right? 3 and 2 here completely gets wasted. The wasted money is percent x of any bank. So what we do is we reduce this wasted by calculating the modulo x. Got it. Got it. Got it. Yeah, this is very beautiful approach. Yeah, this is the thing, right? You can discuss your approaches. Maybe it would be better. Maybe it would. This is something new, right? So yeah, we can also check it by modulo x by reducing the wastage. Okay. How much difficult was he was not getting any efficient way to implement the idea, considering the best and the second best path only. For E, we are going to discuss E2, right? E was actually I was pretty close in it. I just got, I think, lazy for not typing the solution. But yeah, we are going to discuss E. It was pretty good. E was pretty good. Okay, let's actually move to B is rated 900. It might be. Okay. If you guys have any doubt or if you guys want to discuss anything, you can just ping it out in the comments. Okay. Let's move. Let's move. Let's move. Let's move to the third question. Actually, B is rated around 900, but it does not feel like a 900 rated problem. Right, right, right. It does not. Like because it's little trick. matlab, I mean, there might be few cases, right? It just feels little off, right? Just from intuition standpoint, it feels little off, sir, right? Even I think, like, even few of my friends were not able to solve it, even though they were like great. I think, yeah, there's like some sort of blind spot or okay. Let's actually. We also have one more comment here. It does rated 800. Okay. No, it's not 800. I don't think it would be 800. Anyways, let's actually move to the third question. Right. Let's move to the third question. Okay. The secret message. The Bob the genius spy has intercepted an encrypted message. Okay. He assumes that it contains secret information and it actively engages deciphering it. Okay. The note, which has fallen into hands of spy, consists of case strips, each of length n, containing strictly lowercase Latin letters. With extensive experience in deciphering such documents, Bob guessed that the message he is interested in, the deciphering of the note, is also a string of length n. And the ith letter of this message correspond to ith letter of one of the strips. Okay, what this question says is that first thing we got from the question is we have case strips. Okay. So each strip would be like a string, right? Let's say this is a a naught a1 dot 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 an. The length of each strip is n, right? And let's say this is our second strip, b naught b1 dot 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 bn, right? Like this, we have k strips. Got it? And we have this string that we need to decipher, which is actually encrypted. We have encrypted string. Let this encrypted string be s for to making it easier, right? It makes it easier. Let's just name this s, right? And this s string, we have told that for each index I, si is equal to any of these strings, right? It could be it could be ith character of any of these, any of the k strips. Okay, got it, we got it. Okay. And according to Bob, the informativity of a string is defined as the minimum positive integer d, such that a string t of length d exists and s can be formed by repeating t several times. For example, the informativity of string AAAA is 1, and the informativity of string ABAB is 2, and the informativity of string ABCD is 4. Okay, so here we are told that the informativity of string is the least possible string, the least possible size of string t that we could have, such that, let's say the informativity of the string capital S, or let's say informativity of the string p is equal to the least size of string such that p can be made by repeating t several times. So p is equal to t plus example, if here p is equal to a b, the t here, the least possible size of string that could generate this is ab, right? So p here would be equal to t plus t or ab. Got it? This is the informativity of the string, right? The size of tree or the length of tree, length of t, length of t should be least in informativity. Okay, got it. Bob assumes that the note's author to ensure reliable transmission of information. The repeated the data in the message several times. Therefore, more than mm, he believes that a more plausible decryption of the node would have smallest possible informativity. Okay, got it. Help the spy find the message that represents the decryption of node that has maximum possible informativity. Got it. So this tells us that this decryption we have, this decryption we have, decrypted string we have, what we what we mark the decrypted string as small s, right? Will have least possible informativity. Got it? That means that least possible size such that using that using a string of that size we would generate this string. Got it? So this is the entire question. Let's also read the input and output. So again, t, which is the number of test cases, which is actually a standard code forces problem. So as it's a standard code forces problem, this is the standard pattern. And we are given two numbers n and k. Here n is the length of the decrypted string and k is the length of the strips of the paper. The number of strips, right? N is actually the length of strips of the paper as well as the decrypted string. And for each of k lines, we are given n lowercase Latin letters or a string. And we have also guaranteed that n cross k would not exceed 10 raised to power 5. Let's also note this n cross k would also less than 10 raised to power 5. The string, the length of this is n, the length of this, length of small s, which is decrypted string, is also n. Okay, great, 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 great. Question. Right, we have at last we have to find the decrypted string such that it has the least informativity. Informativity is basically breaking bre- taking a string t of least possible length such that that string s can be generated by multiple occurrences of tree or by using tree repeatedly, as we saw here. Okay, got it. Let's actually understand through an example. So this is our first example. Okay, let's copy it. Okay, this is our first example. Yeah, okay, got it. How are we going to have this? How are we going to solve this? We are given, first thing we are given is that each index of the decrypted string would be any of those. So let's say our decrypted string would be of size, this is n, right? And this is k. K are our steps that we had, right? So let's say the R string would be of size n, right? So it would have s naught, s1 and s2, taking the zero based indexing for the string s. This would be our string, right? Yeah, great. So this s naught would either be equal to a or b. Am I right? Yeah, absolutely. Also s1, the first index, the second index actually, would either be also equal to b or a. How I'm talking, we are actually mapping out this. The 1th index would be equal, can be equal to the first index or the 1th index number 1 of any of these case strips. And S2 would similarly be equal to C or A. Now choose the best possible value such that the string we get has least informativity. Right? What possible values can we get from here for the string S? Let's say we choose A, B, and C here. We got A, B, C. Or we could have, let's see, we take A, and A here. We would have A. Or we could have, let's say we took B, B, C. Or we could have B, A. Yeah, I'm just checking like how many random problems. We could have a lot of options there. Right. There would be 8 different options. Right. For each index, we have 2 different options. So there would be total 8 different options. Right. So how many different options we have first? Let's calculate that. So that would be k times n, right? Because for first index we have k different options. For second index we have k different options. And how many indices we have? We have total n indices, right? So this would be equal to k into n different strings. Total strings. Okay. Now the distinction is we need to take with one with least informativity. Would be the informativity for this? This would be equal to 3. Why 3? Because there does not exist any t such that s would be equal to t plus t or something like that. The only t that exists, there exists one t which is equal to abc, which is s itself, right? For this, the informativity would be 1, right? Because we could use t equal to a, and then s would be equal to t plus t plus t. And for this, again, this would be equal to 3 because t would be here, b, b, c. And similarly, we would calculate for each string, right? For this string, as we got info, the minimum value, the least value of informativity is 1. And we got 1 here, right? So that means that this would be our perfect answer, right? So we got here answer. By chance, like we didn't even calculated all of those and we got the answer. There might be case we would not get the answer, right? Let me also see the comments. If you guys have any doubt, you can ping it out in the comments, right? Please seeing it. Okay, okay. So here we got our answer as AAA. Let's actually match it with the problem statement. Is the answer AAA? Triple A? Yeah, right. Okay. They have also like in the example they have also shown this test case where we are using this, then this, then this, then this, and then this. Right, and we are basically creating INF, INF, INF. So here T would be equal to 3 and T would be the size of T would be equal to 3 and T would be equal to INF because 3 occurrence of it would result in a string, the string itself. Okay, great, great. Okay, so again, let's actually use our approach, which is now we are going to find the brute force, right? So what's the brute force here? So the brute force approach would be to find all strings, and then calculate informativity for each string, and then choose the least possible choose the string with least possible informativity. Least possible informativity. What would be the again brute force approach? This beautiful thing about brute force approach is it works. It will work. It will give us the answer. This is the thing we could do. But is it optimized? Okay. How much time would this take? This is going to take k into t n times, right? We just calculated here. There are total this many strings, right? Right. This is actually exponential, right? This is not going to work. We know that, right? Even part is not going to work. Okay. What about informativity? How much time does it take to calculate informativity? It takes like we haven't actually discussed this part, right? We don't know. We can try for each, let's say this uh, subvariant check, can we calculate it or not, and then we'll move forward, right? And then we have the, so this is the easiest part, right? We have to calculate with least informativity. First, actually, instead of finding all strings, let's actually check if we could build the answer from here. How are we going to check it? First, let's check how are we going to calculate the informativity. So the brute force approach for calculating informativity is take any prefix and see if we can, if t is equal to prefix, can we create the string or not? If we can create the string, that's the answer. Otherwise, it's not the answer, right? The first prefix we got would be the one with the least size, and that would be our answer. How much time would this take, right? For taking the prefix, we are going to, let's say the prefix has some size, let's say m, and we are going to basically iterate again and again to check. So each check would take us around 9 n operations, right? The maximum or the this m would go from 1 to, let's say for worst case n minus 1, right? Or let's say we stop it by n by 2, right? So this accumulation here would be 1 comma 2 comma 3 dot 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 n by 2 into n. we can actually calculate it. This would be n square roughly. I'm just roughly calculating it. This would be n into n plus 1 upon 2 into 1 upon 2. This would be n into n plus 1 upon 4 into n. This would be around n cube. Just for calculating informativity. Okay, that's not good, right? That's not good. So what we could do, what how can we calculate here? So let's first talk about t. What are properties of t? Like we know that s are the string that we are finally would have would be around this. It would be having some number of t's, right? So we can say that the number of t's we have would be factor of the length of this. Let's say its length is n. So number of t's we have, number of t or number of string would be factor of n. Yeah, we can completely say this because if its length, because if its length is, let's say, x, right? So here we are, for the final length we multiply x by multiply x with some variable y, right, to get n. So here x and y both are the factors, right? This is how factors are made, right, or divisors are made, right? Being more blunt, these are our divisors, right? So number of t, the number of t we could get would be factors of n. The number or different sizes of t or different lengths of t would be equal to factors of n. Is this correct? Yeah, this is our first observation. Okay, yeah, this is correct. Okay, great. So what's the next step here? Right. Instead of checking for all numbers from 1, 2, 3 to n by 2, we could just check the factors of or divisors of n. Divisors of n into n. Right? Yeah, great. Yeah, exactly. Divisors of n would be around log n or something around that, right? So this would be n log n. So that's actually pretty much efficient. Someone commented that I tried with n into n to the power k possibilities and got TLE. Of course, you are going to get TLE, right? Why? Because here n into k is 10 raised to power 5, right? But let's say even n is equal to 100 and k is equal to 100, right? We cannot calculate for each and every string, right? Because k 100 to the power 100 is a very large number. This will surely give TLE. This will take days to months to years to basically, these many operations can never be calculated, right? We can never try this for these constraints actually. Great, but you at least tried. You thought you went till there. Great, that's great. Okay. Now okay. We got that the different lengths of t would be factors of n, right? So we calculated this would be our divisors of n. So now we could calculate informativity very efficiently, right? We can calculate it in n log n. Now we can calculate this, but we have to still find out what would be the string. Like we have to still make sure that we have calculated around all the strings. So how are we going to calculate this? So let's again take the example we had, just ABC and BAA. So, so, what we could what we could do here is for every like this. Hope this part is clear, right? What is the rating of C? I think C would be around 1300 to 1400 or something in that range. Yeah, that's my take on C. You never know, right? You never know. Okay, okay. Let me just plug in my charger and then get back to it. Any doubt, you can actually ping it out in comments, right? Okay. So what I thought was, anyhow we cannot go for k into the power n, right? Because this is too large. What if for each factor, of n, or we could say for each size of t, size of t, we check if a string exists or not exist. Got it. So this is actually very pretty way. So what are the factors of 3? The factors of 3 are 1 and 3. So first for size 1 we check if we are able to make such string or not, and then for size 3 we are going to check if we are able to make such string or not. And how are we going to check it? Let's say if size is fixed, size is 1. So that means that, let's say this is our string s naught, s0, s1, s2. So this would be equal to this, then this would be equal to this, right? So we basically figure out, we just have to care for this index, then this index, and this index, right? There is one more observation here, right? Again, this would come, we could actually check for each available character we have at s naught, right? Again, someone might think, okay, but Devansh, there are k different characters, right? K different, we have k different strips. There might, this character might be different, this might be different, right? For each k character, if we check it, the time complexity would be k into n, something around that, right? Because we are checking for uh good few segment, right? So this would be k around, and this would again give us TLE. But something, again, the second observation here is, there are only 26 alphabets. So we had to only check for these 26 alphabets, right? We don't have to check for this, k would not be here. This would be 26 into n, or whatever time. This is actually n log n or something, right? Whatever time it takes to basically calculate the uh, whatever time it takes to basically calculate the uh, different strings. This log n is basically the number of divisors or something, right? So this is not actually even log n, but yeah, let's assume this. Okay, number of devices and something, and then this. Okay, okay, got it. So this key would be turned to 26, and then this would be easily be executed in the given time. Can easily be calculated in the given time. A very good example would be, let's take n equal to 6. Now s here would be s naught, s1, s2, s3, s4, and s5. The divisors here, or the number of different sizes of t we could have, a 1, 2, 3, and 6. So for each size of t, we check. Let's say we are at size 2. Okay. So what we do is we make segments of 2. And for this is the first index. We check if this is equal to this, if this is equal to this. And if all these three are equal to A, then we check it for B, then we check it for C, then we check it for D, and we go all the way to the Z, right? If any, all these indices are equal to A, we move to the next indice. And if all these indices are equal to any of those alphabet, we move towards next. If this is satisfied, that means that divisor 2 is satisfied. Then we break, because this is the least amount of least size of t we could get, right? Or the least informativity we could get for any of the string. So this is the solution for it, right? So basically what we do is we iterate for each length of tree. For each t or each possible length of t, we iterate. We find if the length of t is 2, that means that this is our t, and this is our t, and this is our t, because we are going to keep repeating it. And then we check the first index of each should be equal, right? So we check if the first index of each is equal to a or not. Then we check if the first indexes of the second index of both is equal to any of those alphabets or not, right? Right. This is the entire solution. It's very beautiful, and it's like very good question, right? So this is how we calculate it. So what's the steps? What's the solution steps? What's the implementation steps? First, we need divisors for each number, right? And then for each divisor, we are going to check for all alphabets. For all alphabets, can t of that size exist? For all alphabets at all indexes, size exist. And then we break if we cannot find out. This is the entire solution, right? Let me actually go through my code, right? This was the entire question. See how far we have come from, right? First we discussed the problem, we got case steps, we this is encrypted string. Ith character of this is actually one of the ith character of this is actually ith character of any of, it could be any of the case steps, ith character of any of the case steps. Then we also found this term informativity, and then went to the we found the least possible, we got to know that we have to find the string with least informativity. And then what we did, we first understood the problem, we understood the edge cases, and then we went forward. First, we tried the brute force approach. In the brute force approach, we came to know that even finding all strings is going to take k to the times n. So first, we actually focused more on informativity. When we went there, we got to know that we just have to calculate for all factors of n, because these factors eventually the sizes of t would be equal to n, right? So the, the size of t would always be a factor. And then using this knowledge, we came to know that if we make the segment of the size of the factor, let's say we assume that if this was t, and if this was t, and if this was t, right? That means that the first index of each t should be equal to, it should be equal. We check if all these three are equal to a, b, c, d, or like any alphabet. If these are true, we move to the next. Otherwise, we break and move towards the next divisor, right? And then we came to our solution. Let's actually go through the code. Again, this is my template, just ignore it. Here's the beautiful part. First, this is the vector where we are storing what can these two be equal, like what possible values each indexes can have. This is what this vector is storing, right? For example, let's say we had a, b, and c, d. This vector will tell us that at first position we could have first and the third, like we could have a as well as we could have three, the third character. And then we move forward, right? So this part tells us that this is here, I'm just calculating it. This answer key is our actual answer. I'm actually in the first iteration, I'm just keeping it, let this answer could be the first step, right? I'm just initializing it, but later we are actually calculating it. So this is how we calculate here. So this in tie into factors, and this here we have calculated for each factors for each number, right? Pretty standard way. And then we move forward, right? What we do, we check for each of these, we check for each of this segment, right? For this segment, we check from 0 to less than I, right? This would basically meant a segment. And then what we did was we basically check for each indice, like if we are at zeroth indice of our current segment, then we check for zeroth indice for each segment. How we check it? We keep a while loop. This ij tells us for another segment. We basically increment this ij by I, and then we move forward. And what I did here was basically I did it with, and I like the approach I told you was actually very easy one. We could check for each alphabets. What I did was I basically set the bit, right? For let's say for each indice, we could have certain number of numbers, right? Let's say it had one. So what I did, I set the first bit, and it didn't had B. I made this zero. And if had C, I made this one. And similarly, the first bit of this had 1, had A, so this would be 1, had B, this would be 1, and had C, this would be 1. And similarly for C, this would be equal to, it had, let's assume it didn't have A, it didn't have B, it had C. So this would be equal to 0, 0, and 1. And what I did was I basically did AND of all these values. Right, I got this. If there are no common numbers, if there is no common set bit, this would result in 0. That means that we could not have any character which is equal to any character which is available in each of these indices, right? This means that we have a character which is equal to any of these indices. Let me also show you my code. This is the part where I AND it. This is the part where we calculate the number, this number, right? And this is the part, if this is equal to 0, that means that we don't have any common character, so we break. Otherwise, we have a common character and we find it out, right? And what would be the, like this, the value of the character would be the its position from the last, right? A plus cnt is the position from the last bit, or the least significant bit, lsp. This is equal to 2, so this would be a plus 2, and we did character here, use character here, so this would be equal to a plus 2 would be c. But we can actually check it for each character. This is like also fine, right? This is actually little bit, more optimized. I wouldn't say more optimized, just actually really this is fine too, but yeah, we could do it either way, so it wouldn't matter. And then we check if for this I there exists some t. If there exists, first we put the answer here, and then we basically push it, pu- we make the entire string, right? We have to make the entire string as we got the t, right? So now we have to do t plus t plus t plus t, right? We have to basically add t again and again. If we have Python, we could have just multiplied it, but as we are using C++, we are doing it in the manual way, and then we are printing the answer. Hope this sets up. Hope this is enough. Right, right. This was the journey for the third question. If you guys have any doubt, you can ping it out in the comments. Even after the contest, we are going to discuss it. I would be like, I would be checking comments after the contest too, so it wouldn't matter. Got it. Got it. Let's go for the problem D. Okay, let's go for the problem D. So I'm actually checking comments. If you want to type something, if you guys want to ask something, if you guys want to. Sutanu said, okay. Anything else? If Let's actually move to the fourth question, the second last question. Waiting for Dia. Let's actually understand the dth problem. Yeah, on to the dth problem. Yeah, okay. You are given a size n into m, where each cell contain either 0 or 1. The task is to divide it into two parts with cut that goes from top left corner to the bottom right corner. The cut lines can only go right and down. Let A be the number of ones in the upper part and B be the number of ones in the other part. And the goal is to maximize the value of A into B. Believe me, guys, when I read this question is very easy than B, straightforward than this. Just there is just one observation here. Let's actually discuss this problem. So we are given a table, have n rows and m columns, right? And every value here would be either 0, either it would be 1. Ta-da, 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 ta-da. Okay, great, great, great. Second thing we have told is we have to cut the subarray. What does it mean? It is very beautifully depicted in the example, right? So here we have this subarray of size 5 cross 5. Here are the values. So we start from the topmost point and we go to the bottom right point, right? First we cut here, 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 here. So this, while doing this, it makes two parts of the grid. This is the first part, this is the second part, right? We make the two parts of the table or the grid, and then the answer here would be, the answer is number of ones in first part, in one part, number of ones is common, right? Into in the second part. Okay, great. This is the answer. Okay. What we need for the what we need to do to the answer, we need to maximize it. Okay, great, great, great. So basically this question, let's actually say here, we can do any number of cut, right? And then after doing this cut, we have to make sure that the number of ones here into number of ones here is the maximum, right? Let the number of ones in first part be equal to A. Let's symbolize it with A, and the second part be equal to B. So what we need to, let's actually, this is the entire question. Hope you got it, right? So this question tells us we need the maximum value of A comma B, A into B, sorry, right? Let now let's actually see the problem, right? Let's first start with some example, right? How we can cut this? How we can cut this? Let here A is the number of ones in, let's say, upper part of the first part, B is number of ones in the second part, and X is total number of ones. So X is equal to A plus B. Right. What we need to do is we need to maximize A into B. Let's say we made some cut. We started from here, we made cut, this, and thus. So here A would be equal to 2, B would be equal to 3, X would be, again, X is again constant 5, A into B is 6, right? And let's say we made some other cut. Let's use the same array here. 1 1 0 0 1 1 0 1. right? The same table, we did something like this. We we cut through it like this. Now here A is equal to 4, B is equal to 1. X would always be equal to total number of ones, which is A plus B, right? So here A into B is equal to 4, right? So the best way among these two ways is this one. Obviously, this is one, right? So there are actually one observation we have to make. We have to basically make this maximum. Let's forget about it. Let's forget about the cut later, right? We have to make this maximum anyway, like anyhow. The first observation that might come to your mind, actually I also read the input and output. Again, the generic T, which stands for number of test cases. Then we have N and M, the number of rows and columns. The jth number in the ith line is aij, so the standard way of displaying a grid. And then we are guaranteed that n cross m would always be less than equal to 3 into 10 raised to power 5. Let's actually put this into the question bank. The 3 n cross m is always less than 3 into 10 raised to power 5. Okay, great. So again, let's actually go with our standard flow. What would the brute force approach for this? Right, let's actually type it here. What's the brute force approach for it? The brute force approach would be actually calculating all possible values, right? All possible values of one, all possible paths, right? So let's say we are in this, we could go here, we could go here, we could go here, we could go like here. There are like all possible values, right? But how are we going to calculate it, right? How are we going to calculate it? This is actually even brute forcing it is actually a little harder, right? So, like if we are able to calculate all possible values here, what we could do is we could get maximum for from them, right? Yeah, we could. So, but this is actually a really headache. Even brute force is even calculating all possible paths and taking its sum is great headache. How we could do it? We could actually use a three like a for loop using 3D DP kind of thing, right? In which we have I, J, and K, where K is the sum. I'm talking about brute force here, right? Where K is the sum. Let's say we are at I comma J. At every move, we have two different choices. Either go here, either go here, right? At every move. So we could go there and then we could calculate the boundary, and then we might even store the number of ones above this point, number of ones above this point, and use that, right? And the final value, we need the maximum value of A into B. Okay. Let's actually discuss one more thing. What would be the maximum value of A comma B if we have X number of ones, right? It's clearly stated fact that the maximum value would be somewhere between X into 2 into the remaining part of X. If it's even this, otherwise it would be around X into 2 into X minus X divided by 2, right? The middle part is always the maximum. Do we agree here? Do we agree here? You can actually take any number and calculate it using it. Right. So this is our first observation here. We understood like we have some DP we can do it by dynamic programming, but this is going to take too much time, right? This would be n into m into the sum, and the sum would be around the maximum sum is around n, right? So this would be nq, which is actually pretty great, right? N into m is less than we could do it at max n square, which is n into m, not even n square, right? So yeah, this is the brute force approach. But let's actually just understand. Let's do some maths here. Yeah, this is the greatest number. If we want the greatest number here, the best A would be x by 2, and B would be equal to x by 2 or x by 2 x minus x by 2. Okay, great. Now the question arises here, if we know the best A is this, either way, if x is even, if x is odd, either way, best A is this. Can we do something that we cut such that we get x by 2 ones in the upper part or the first part? Can we cut like it? Cut like that. Believe me, if you if you think you can think about this, you can actually pause and think about it. This whole observation, this page is the entire answer, where the entire answer lies. Can we cut like it? Okay, great. So let's take this number, this vector that this table that we were using earlier. Here we have z- 0 1 1 0 0 1 1 0 1. Right. X here is x here is equal to 5. So a, the best possible a is equal to 5 divided by 2, which is equal to 2. Can we cut some, can we do some type of cutting that gives us 2? Let us think. Let us start from the last side. Right. We know that here at this point we are at here. Right. So that means that while transiting, we must be somewhere, we could either transit from here, we could either transit from here, we could either transit from here. Right. Yeah, yeah, absolutely. So what we could do is, what observation I made was, I start from this. I check how many ones can we take this one. Yeah, we need two ones, right? Yeah, let's say we took this and we took this. That means that we have to take this, we have to cut this part. Do we need more ones? No, we don't need. So let's just exit it. Right. In this way, we would always have an option to cut like that to get a perfect A. If we get a perfect A, B would be by definition perfect, right? Because B is x minus A. This is by definition, this would be always be perfect. So we just need a way to cut such that we get a number of ones here. So for that, we could just start from last. We could find the we would iterate from the first row to the last, and let's say we got a requirement here, we would basically from the previous array we would go to the starting, and we will not take any element and we will move forward. So this is the solution for it. Right, this is the solution for it. Let me actually use one more vector, and let's use this example. Here x is equal to 6. So a would be equal to 6 divided by 2, which is equal to 3. Right. Yeah. So we need 3. We start from here. Can we take this? Yeah, we can. Can we take this? Yeah, we can. Can we take this? Yeah, we can. So we actually took the whole row. Now we go here. Can we take this? Yeah, we can. Can we take this? Yeah, we can. Can we take this? Yes, we actually go to the whole row again. Can we take this? No. So basically, we wrap up and we don't take any elements here. Got it. This is the entire solution here. And at last, what we need is, we need for output, we need the maximum value of product, as well as we need the end characters, which basically tells us what move did we take. We could use this to backtrack, right? We could use this to backtrack. How many elements from here we take? We take 0. How many elements we take here? We took 3. How many elements did we took here? We took 3. For backtracking, we would go 0, the difference. Initially we were at 0, right? This is for the rows. Actually, we are iterating row column by column. So the do we have to go down? Do we have to take element? No. So we just took right. we are just going right. So we just push R into the string. Now, when we reach here, we have to take three elements, right? So we have to go down three times. One, two, three. So we push down three times. And then as we are going to the next element, we are pushing R. Now we have to take three down, three more elements, right? But what's the difference between two? The difference between them is zero. So we are going zero steps down. So we are not going to push any D, but as we are going outside, we are going to push R. But at this, right? So here we push it R and we reach here. And this is our final string, right? And our answer would be again A into B. And A is x divided by 2 and B is x minus A, or x minus x divided by 2. Got it. This is the entire answer. Yeah, this was actually pretty easy. I'm also checking comments if you guys have some observation or something regarding it. So yeah, this is how it entirely worked, right? Let me actually show you my code. This was it, right? This was it. This was it. Yeah, this was the entire solution. Yeah, yeah, here. Here I'm just iterating from last to first. So again, we are taking input. This sum is total number of ones. Here this is x, right? And this OC is the occurrences we are capturing, right? The occurrences we are capturing, which is this. This is the OC for us. Occurrences we are capturing or the lengths we are capturing. I'm just iterating from the last to the first, the last column to the first column, and then I'm just checking if the requirement is ended. If the requirement is ended, we end it here. We put the default value. If the requirement is not ended, that means we took the entire row, which is we took n minus 1 elements. And if requirement is 0, we broke. And then we basically check A is equal to n divided by 2 plus, just actually this is our A, this is our B, and the maximum value would be A into B. Here this is both are reversed, right? Just make sure. This is actually useless. This is something I was thinking, but yeah, the optimize is this, and we don't need it. And then we move forward. Just 1 second. Yeah, I just got call. So yeah, this is I was talking about. Then we are just here. We are calculating this string this way, right? If the difference, we are just iterating down to the difference we have. Otherwise, we are just moving towards the right, and then we are printing the final answer. Hope you guys love the solution. Let me also see if you guys were actually waiting for D. This was the D. This was pretty easy. This is how we went. This was the entire journey for D. Got it. Got it. Got it. Got it. Got it. So yeah. Now let's actually move to the killer problem. E, which yeah, yeah. Let's actually also read the problem statements. Actually, uh, Okay, I'm back, guys. I'm back. I'm back. I'm back. Let's discuss the problem E now. Okay, the turtle strikes back. After a heavy training session, we have two guys, Rafael and Michelango, and they decided to order pizza. Great. Today, on the occasion of holiday, they also know today is Sunday. Huh, just joking. By the way, the pizzeria is preparing the rectangular pizzas for n rows and m columns of slices. Each slice has its own unique recipe and flavor. Was he was the first to open the box and roughly estimated the pleasure of each slice. Pleasure from the slice located at the ith row and the jth column is equal to Aij, and it is guaranteed that there is at least one slice that Michelangelo liked, meaning that among Aij there is at least one non-negative number. The turtles agreed that he should eat first, and according to an ancient tradition, he must choose a route from top left corner 1, to the bottom right corner and eat all slices on the route. In one step, he can move either to the adjacent slice on the right or to the adjacent slice below. He aims to maximize the total pleasure from the eaten slice. Okay, got it. Everyone wants to maximize their total pleasure from the pizza slice, by the way. However, Raphael decided to use sauce. Before he chooses a route, Raphael decided to choose exactly one slice of pizza and apply his signature sauce to it. But due to specifics of this sauce, the pleasure that slice changes to the opposite of that slice. If it was previously Aij, after applying the sauce, it becomes minus Aij. After that, knowing that Raphael's choice, he would choose the optimal route for himself and eat all the slices on it. Raphael became curious what would be the minimum pleasure he could have, help him calculate the number. Okay, great, 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 great. So what this problem says, okay, what this problem says, this problem says is that we have two persons, we have this M, we have this R, let the person be M and person R, Raphael and the second one. And we have told that we have a pizza slice of n cross m, which is a rectangular pizza size. That means that it has n rows and m columns, right? And the pleasure he got from each slice is a comma here. This is a 00. So the value of the value at the particular row and column tells us the pleasure he gets from eating this slice. Okay, great. And second, we are told that the guy M starts from the 1, 1, the very first slice, and goes to the last slice n, M. Got it. So he basically starts from here, and he basically eats a sequence of slice. And at every sequence from let's say 1, 1 to n, he could either go down or either he could go right. These two operations are available. And that means that he goes here, and then he basically takes a path and reaches to the last slice. Okay, great. Now the twist here is we also have this R guy, Rafael guy. He can basically add some sauce into any of the slice that would basically change the sign. If he puts a sauce on Aij, it would become minus Aij. So it basically inverts it. If it's negative, it would become positive. It is the magnitude remains same, but it will change its sign. Okay, great. This is also great. So this is, and we are told to find the minimum pleasure this M guy would get. Okay, great, 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 great. So this is the entire question. Initially, we are given this rectangular pizza box, whatever this is. we are given n into m slices, where each slice gives us pleasure aij. This is a pleasure. We're also given that at least one of them would be positive, right? At least, fifth point, at least aij, any one aij would be greater than 0, or this is positive. Okay, this is the entire question. We have to find the minimum pleasure this would get. By the way, the M guy knows where did the Rafael or the R guy did the operation, right? Right. We are simplifying the question, right? This is the simplified part of the question. Let's also go through the constraints of the problem. We are given n into nm, right? Here n is number of rows and m is number of columns. Okay, great. T is number of test cases. Again, the standard part. And then we are given aij, where aij is the value for each. This is the pleasure for each slice. And there is at least guaranteed that one non-negative value or one positive value, or this could also be 0, exist. Okay, great. So we have to find n cross m would all n into m would always be less than equal to 10 raised to power 6. N into m is always less than equal to 10 raised to power 6. Okay, great. Anything else? No, nothing. Okay, got it. So the problem here is, in simple words, is that we are given pleasures. We have to take this part. And our guys does some flip, right? He does some flip. And M knows what flip he has done, and now he has to calculate the path, right? So initially I was thinking, like during the contest, I was thinking around taking one or two optimized path and then calculate it, right? And then find the answer or something, right? So the observation, that's also a very good observation. Let's actually check the first problem here. So for the first problem, this is our first test case. We could start from this. We are always going to start from me actually. 1 minus 2, 3, 4 minus 5, 2 1.
Hello, hello, hello. Hello, hello, hello. Yeah, okay. I think now it's working. Thanks a lot, Kevin. Thanks a lot. Thanks a lot, those who actually informed me that my mic is not working. Okay. Let's actually jump. Let's not actually waste any more time. Yeah, okay. I think now. Okay. Let's actually begin where we left. Okay. So yeah. So yeah, we left here. So, what we have discussed it, we can use, uh, l- let's say we have this array. So we can take this path. Initially, this was positive, right? But this is the optimal path. This would actually result in 1 plus 4 plus 1 plus 6 minus 1. So the value for this would be around 11. This is the best possible path. But what would the person R would do? He would flip this one and this would turn negative. So the final for this path, it would become minus 1. But let's say he flips it. It's not necessary we will you take this path, right? We can take this path. If we take this path, the answer would be 3 and we will take this path, right? Yeah, we can always take 3. So the minimum answer would be 3. If we hinder any of these elements, this element or this element, we can still take this path, right? If we hinder this element, we can still take this path, right? So here the thing I wanted to say is if we are going to flip this, we can take some another path such that we could maintain the sum. We could get a better value, right? The best possible path, we could take some another path that doesn't contains the flip, that doesn't has the flip. Okay, great. Otherwise, there might also be chance for this grid, for example, right? For this grid, this was the only positive number. Remember that we always have one positive number, at least one positive pleasure points, right? So what we could do if we took this path, right? If we took this path, this would actually result in minus 2. But what if we flipped this one? Then this would turn negative, but we can still take this path, right? And this would result in minus 4. Let's take this was minus 4 and minus 4. And instead of plus 1, we turned it to minus 1. We would still take this path, right? That means that we still took the same path that had the flipped, right? So this was our first observation from first test case. This was our second observation of second test case. These two test cases are already given, right? We have just modified this a little bit, right? But these two are already given. Okay, great, great. So what came to my mind is let's actually, whenever we solve any problem, we go step by step. And the first step is always to solve it using the brute force. Always think, can we solve it use the brute force technique? So the brute force technique here is, we start from, what we could do is never know which element we are going to do the flip. Is it correct? Yeah, this is correct. But we know that we can always flip the positive element. Why? Because we need the minimum value. We need the minimum pleasure that the that guy could have, right? The R needs to minimize the value, minimize the total sum. So we would always flip the positive value. And it's given that there is always one positive value. So that means that we will always flip the positive value. We can do this. So this is a third observation. We can flip the positive choices or the positive pleasures. Right. So what I would say, can we calculate the path? Can we calculate the maximum path? Yes, we can either use Dijkstra, like we could actually pretend if this is a graph and we could use a Dijkstra, or otherwise we could Also use dynamic programming with it, dynamic programming with recursion. There are couple number of ways, right, that would help us to go from the first element to the last element. We will discuss these, don't worry, don't worry. Right. So after, let's say we have some way into calculate from first, go to the first element to last and find the best possible sum, right? The maximum possible sum, and that takes n into m time complexity. Okay. How it this work, right? For this, let's assume we have this array. Let's actually take this part, take care of this part. Okay. We could keep a DP dynamic program like a 2D DP ij, which tell us the best possible path. We could use recursion plus TP here, right? This is how to calculate best path, best sum for a vector, for a matrix, let's say, right? So we could use recursion plus dynamic programming here, in which we start from the first element and then we have two choices. We can go either this and this. So our recursion would look like, again, like how do we, like in today's morning lead code contest too, we had this recursion problem. Whenever we have recursion problem, we can use dynamic programming to optimize it. The recursion would look like something like this. The recursion function, we have this in the first, which the row, let's say we are at ith row and the jth column. And what we could do is basically we have two options. We could basically go to the towards the right. That means we could do recursion I plus 1 comma j, sorry, j plus 1, right? We are going towards the right. Or we can go down, right? So we could do I plus 1 comma j, either of those, and we'll take the maximum value of either of those, both recursions, and we'll return this. Any of those, we are basically also going to return the current value, which is a I comma j, plus the maximum of this would be we are going to return this, right? What we are going to return, this value, this, the current value. Let's assume this vector is this entire 2D pizza box is denoted by a, then this aij plus recursion of when we go right and when we go left, when we go down, right? Using this recursion and then optimizing it, right? This value we are returning it, this is equal to, let's say this is equal to dpi comma j. So in this way, we actually restrict the number of recursion to I comma j. How many new values of I we could have? We could have n. How many number new values of j we could have? We could have m. So the time complexity would be n cross m. Right. So here there would be this if statement, if dpi comma j is equal to minus, is not equal to minus 1, or whatever value we have, right? This, let's say this is not minus 1, is dpi comma j is filled, right? We have calculated is filled or calculated, return this, return this, return dpi comma j, right? So this, what this code, this with this pseudo code tells us, that we could basically calculate the best path. Starting from here, we could get the value for it, right? And as we need to do brute force, what we could do is we can apply flips only on positive integers, right? This or this. So we will calculate all different matrices, and we will, for all possible matrices we could have, in each of the matrices there would be some positive number which has been flipped, right? So how many matrices we have? N cross m, because the number of positive integers could be at max n into m, right? All the numbers could be positive, into n into m, which is the time for 1, right? The time to find the maximum path for one, for any one flip, right? For each time or any matrix, right? So this would be n into m into n into m. This n into m is around capital N. Capital N is, let's say this is around 1 is to power 10 is to power 5, right? So this 10 is to power 5 or 10 is to power 6 is the same thing, right? So this would be n squared. So this would not work. But the beautiful part about this entire thing is, the brute force thing is, this is always correct but not efficient, right? This is the this is the most beautiful part about the brute force solution. This is always correct but never optimized, right? Sometimes it's also optimized, right? But in this case it's not optimized, but yeah, it's always correct. Okay, so what we could do now, what we could do, how can we calculate this toll we are taking to check for each flip? How can we basically do it, right? Now let's calculate what all observations we have. The first observation is, we can take another path where the flip doesn't happen. We can take the same path, or we can basically and the third observation is, the flip would always happen on positive choices, right? These three observations we have. Okay, great, great, great. So what we could do is, we have to just optimize this part, right? This part is not optimized. Okay, great. First, let's calculate. What we could do is, for any value, this, let's take the flip is here. The flip is here. Let's assume the flip is here. What does this mean? Now we have two choices, right? Either include this, either don't include this. Right, right. Either we include this or either we don't include this. So, first let's talk about not including this, right? For any value, if we want to not include this, let's actually, instead of this, let's erase this and let's also erase this. For the simplicity, let's assume this is positive and we have choose this element, right? We have choose this element to flip. Now, let's say we are not including this. If we don't want to include this, that means there is one more observation we have to make, is that while we are calculating path, let's say we took any path, right? We visit each row or each column only once. Yeah, that's true. We visit each row or column only once. Yeah, that's actually correct. That's fine. That's fine. That means that as we visit there, that means if we are not including this, that means we have to take path that either goes from the left of it, right? The transition, some there would be a point, right, where it would reach row equal to 2. This is the second row, right? We would want, whenever it reaches row equal to 2, right, it makes its transition. The thing is, we visit each row at least once, at least, because we could just drag into the column again and again, right, and still be in the same row, right? So yeah, whenever we are at this point, right, what we could do is, to miss this point, we could either go from the left side of it or we could either go from the right side of it. Is this correct? Yeah, this is absolutely correct, right? So let's say I'm iterating each element again, and let's say I'm iterating each element. For this element I can find the maximum point, right, from all those values which are at the left, that we used, and then we transited down, right, and all those values on the right that we use and we transited, right, we transited down again. Instead of using this, we don't include this. We could calculate all possible values for that, and then we could move forward. Got it. So what we could do is, this is our first possible observation, right? So what I meant to say is, basically what we are going to do is, we are going to calculate this in constant time, or basically we are going to iterate this once, and we are going to calculate for each value. What if this was the flip, right? Or what if this was the flip? Then we don't include it. If we are not going to include it, then what's going to happen? And if we are going to include it, then what's going to happen, right? And to calculate what's going to happen if we include this or not, if we include this, what is going to happen? If we include this, what is going to happen? This path must have some value, right? This path, the entire path must have some value, right? First it was contributing plus 5 here. Now it's actually not contributing, it's actually reducing minus 5 here, right? So we are basically going to reduce it twice, right, of the original value, for every positive value here I'm talking, right? So what we could do here is, basically, let's take two dps here, 2 dp from origin, from 0 comma 0, and dp from ending, or from n minus 1 comma m minus 1, right? And we could use these two. Why are we using these two, right? When we are basically flipping it, when we are not using it, what we could do is, basically, one, to get the maximum path, and to use this flip specifically, what we could do is, take the sum, maximum sum we could get, if we get maximum sum we could get if we start the path from the beginning, and take the maximum sum we could get if we start the from path from the end, and then we could add those path, right? Is this correct? Yeah, this is absolutely correct. And how are we going to calculate the maximum sum of the path starting from the start to any element? We could use this logic again, right? We could start from the first element, and we would calculate the dp from 0 comma 0, and then we could calculate from dp from this. Basically, this dp tells us the maximum value of path when we start from ending, max value when we start from ending. And this tells us maximum value of path when we start from starting. From starting. Right. So this is how this entire workflow would go. Right. And why are we using these? Why are we using these? Let's say we took a path. For every element, what we are doing, we are just iterating every element. Let's actually just use use, like, basically type the vector again. 1 minus 2 3. Let this be 5, let this be 4, let this be 6, let this be 7, 2, 1, 3, 2, 1. And we are just basically iterating each element, right? We start from this element, this, and we are going to calculate, if I did flip this, what would be the maximum value? Okay. Again, for each flip, we would either include this, or either we would not include. Not include. If we include this path, let this dp from 0 comma 0 is dp start, and this is dp ending, right? And from let's say this is the maximum path here. This is not, I know we have to take 6. Let's assume, right? If we are including this, the answer would be dp start from, this is, let's say, this is second, this is 1 comma 1, right? Plus dp ending, which is 1 comma 1 again, right? Sum of this, and we have flipped this, right? We have flipped this. So when we flip this for this part, it would give us 2 into 2x, 2 times into ai, this is j. Oh, this is 1 actually, sorry. A1 into 1. Twice, right? Each time we reduce it by twice into 2, because we are, this is overlapping, right? Right. Hello. Yeah, right. So this would tell us, gives us the value of when we didn't include it. We included it, sorry. And what if we didn't include it? If we didn't included this, that meant, let actually again place this here. 3 7 4 6 2 1 3 5 2 1. Again, if we didn't include this, that means we took some path like this, which crossed either before, either backward, right? So like for this path, we would have to check, let's say we cross from here, from this point, and then we cross from this point, we would check for each point, right? But again, that would increase the time complexity, right? The time complexity, again, for any point, this would be m. So this would be m into n into m. This would again be, actually this is pretty efficient than last one, but this is again inefficient. So what we could do, we could keep a suffix, and here we would keep a prefix array. And these prefix array would store for every value if we cross from here, and this suffix array we will calculate from every value. If we cross from here, if we cross from here, what would be the best possible value? Crossed means that went from this and we did here. We crossed from this, we did here. Every row needs to be crossed, right? Every row needs to be crossed, right? So this is how we do it. This is how we do it. Either we cross from before, either we cross on the right side. And how are we going to calculate it? Let's say we cross from here. What would be the value? The value would be the starting point, like the starting, how we went here, right? Plus, how are we going to reach here? Because it will have 2 points. It could either go right or it could either go down, right? So if we took the down path, and this would actually be for prefix I comma j is actually dp starting I comma j plus dp ending I plus 1 comma j, right? For dp prefix I actually, right? This would be value for this instant. Otherwise this would be this max of this or prefix I minus 1. Similar goes for suffix. So suffix I, this would be equal to max of suffix I plus 1. here we are actually not including icon this we are not including this array, so we are calculating the prefix part if we took some path from the prefix, and if we this will make sure, right, that we chose the leftmost part, like we didn't include it because we are not going on right, we are going towards down, and once we go down we cannot go up. Okay, this is the intuition, this is the visual intuition here. Suffix this or dp, uh, ending of I comma j, j here, plus dp starting of I minus 1, right? 1 second. I minus 1 comma j. Right. Got it. So we will be using these two, as well as we are going to using this included formula, and then we are going to find the answer. Got it. Then we are going to find the answer. This is the perfectly beautiful solution for it. Got it. Got it. If you have any doubt, like if you guys have any doubt, I'll be seeing the comment section, as well as I'll also be replying in the comment section. Right, now we'll go through the code. Let's go through the code once. Let me bring the code actually. While the stream began, there was some issue, so we couldn't submit it. But yeah, just few minutes. Just 1 minute actually. Let me just drink water. Yeah, this problem was actually good to digest. That's why, like, the code is very beautiful, believe me, guys, because I actually took some effort. Like, I started from the last question, then okay. Yeah, for code, let's go code chef, compiler. Yeah, let's go here. Running compiler, that wouldn't matter. Yeah, this worked, right? So here is our code. Let's understand this. Right. So first we are taking input. We are assigning. We are just taking this. This is an input. What we did was we took in the start yard. Okay, this code has been reformatted just for explanatory purpose, because the initial code that I wrote was absolutely garbage because it was during the contest, right? I hope you guys understand. Like, I just wanted to, like, get it done, but yeah, I it was done after the contest. Anyways, this is the solve from start, right? Again, the same DP plus recursion, right? And again, this is our both We could either go down with the, we could either go, how are we going to go here and there, right? The maximum sum from 0 comma 0 to I comma j. This is for solve from end. What happened, like the maximum sum we get from the end, this recursion plus tp here again, and then our best part here, we are iterating the array. So first we iterate each row. We find the left best and the right best. Left best and right best are the numbers here. Here, these part. The left best, the prefix here is the left best. The suffix here is the right best. And what we do here, here we are calculating the left best. We are using the same formula that we used, and the same formula here too. And then finally, what we do, if we avoid light, that is we use the left best method, we are using here left best, otherwise we are using the right best. These checks are just if the, let's say if the element is the first element, there is no left best, right? That's why these are the checks for it. And then if we are forced to take that part, again our own formula, and then the maximum for it would be our answer. So this is the entire solution for it. I'm going to actually, all the summations you will get it in the chat box, right? So this marks end for our stream. Yeah, do subscribe, do like. If you have any doubts, you could put it in the comments. I'll surely read it even after the contest, right? And like if you like the video, if you think, if you have any feedback, you can also like comment it, right? And yeah, that's all from my side. Hope you guys liked it. All the submissions will be in the comment, right? Do comment your favorite problem, right? Today, like I think B was little trickier. C was also good. D was not that good. E was good, right? A is again just the standard A, div to A, right? So yeah, let's actually end the stream. Hope you guys liked it. Do share your thoughts in comments. If you have any better approach for any other problem, do share it, right? Okay, let's see ya.